In this module, I want to explain a particularity about multimedia data. So multimedia data are things like videos, images, audio, speech. And what's interesting about multimedia data is in order to record videos or images, you need a camera, and in order to record audio or speech, you need a microphone. So in general, multimedia data is sensor-based data. And what's interesting with this sensor-based data is that you can't really compare it one-on-one, right? So if you say image A is image B, then you usually don't mean you compare each pixel like exactly the value. Because if one pixel would just, change a little tiny bit, a human would still say these images are completely identical. Despite the fact that a computer would say, there's like one pixel is like one bit off. So that's one difference. Another difference is that, for example, searching through multimedia data becomes harder, and also, and most importantly, compression of multimedia data becomes harder. And the same goes with recognition. For example, recognizing faces is much more difficult than recognizing the word FAC. So before we continue here, let's introduce, we have one type of data, which is sensor-based, the other type of data, which I will call man-made. I call it man-made because typical data that can be directly compared and compressed is, for example, text, right? So you can just type stuff, you can search through easily, you can easily go and edit things in and out, and you can compress it really well too using regular entropy compression. Other data would be that works the same way would be drawings. Despite the fact that they're images, we can really work well with, let's say, a vector drawing and compress it and compare things, and it becomes geometry, but it's much easier than working with these noisy images. And we will talk about the whole thing in a bit. And also, usually, the typical thing is like, let's say, like budgets, right? Stuff like that. So man-made numbers you can easily work with. So the question is, how is it that the sensor-based data is so much more difficult to handle than man-made data? Well, you could say, hey, it's man-made versus nature-made, and that's of course the point. But let's explain this a little better. So let's talk about the sensor-based. So we had this equation before, which is called the Helmholtz free energy. And that equation is, again, A, like R byte, is U minus TS. And now let's take the example of a camera sensor and reinterpret this formula so it explains to us what's going on with, let's say, image data. Well, the first thing we need to know is T is certainly our camera noise. Right? And then we can put S as the pixel, in the universe, the actual pixel, right? The pixel that we wanted to record. And that pixel is convoluted by a camera noise. And then U, for us, just for technicality, would be what's called a D65, for example, the reference white. This is the maximal excitation of that sensor, the reference white, the brightest it can record. And then out comes A, which in our thing is the actual pixel, the actual measured pixel, right? So the thing that we see when we work with this data. And that's interesting because we can forget about this U minus for a bit, but what happens is that we end up with a convoluted signal, which was we have TS, right? So we have noise times entropy. So now the issue is, if you try that, for example, use an entropy encoder on the actual pixel, and you basically do something like zip of, let's say, face picture dot bitmap, which is a direct recording of the pixels, you will see that your compression ratio is something like maybe 1 and 2, right? If you, however, JPEG the face bitmap, you will see that the compression ratio is something like 1 in 10, right? So you basically each pixel only needs 1/10 of a bit. So how does this work? What does JPEG actually do? So let's take a look. JPEG takes the actual pixels and then applies a DCT and other things, but ultimately what it does, it provides a high stop filter, right? So basically the high frequencies are weeded out. And then it applies an entropy compression, just like you zip. And then if you undo it, you'll see that you have, of course, a loss. But what's interesting about this is this high stop filter, because what does this actually do? Well, we said before, when we work with an image, we have TS, right? So ultimately, we don't know the exact function of the camera noise. But what JPEG does, it says, I don't care that much what the exact function is. You just give me an indicator. For example, a Q is a quality, a quantization factor. And you can take the slider and then just basically come up with some T approx, right? What it does is we quantize, right? We divide by the high frequencies. So we divide by something that emulates the temperature noise. And so TS divided by T approximate obviously becomes S approximate. And S approximate is just an entropy, and so can be compressed really well using typical entropy compression. So when we have man-made data, we can just use tools like zip, which actually implement something called LZW, and other mechanisms. And when we have sensor-based data, we need to use stuff like JPEG, MPEG, or MP3, with all these names. And the reason for those is that they need to quantize the noise out first, and that cannot be done accurately. That can only be done approximately before an entropy compression can be performed. More importantly, this generalizes. So we should, whenever we handle image data or any other sensor data, always quantize the noise out first, because that helps us actually deal with the information rather than with noisy information.